Distributions of transformed random variables. Example. Suppose x is a continuous random variable with a given probability density function. Suppose, for example, it's uniform, so the density function f of x is 1 when x is between 0 and 1, and everywhere else, little f of x is equal to 0. What's the cumulative distribution function of y equals x squared? When we square the random variable, how do we get the cumulative distribution function of this new random variable y? Well, it's easy to say what you don't do. You don't square the density. You don't square the cumulative distribution function. We're interested in the distribution of a function of a random variable. And the first step is to identify the cumulative distribution function of this random variable, f of x. Capital F of x is the integral from 0 up to x of the density 1 dz, which in this case turns out to be just x. F of x is equal to x when x is between 0 and 1. The next step is to find the cumulative distribution function of y. So write down what that means. The probability capital Y is less than or equal to little y. That's the definition of the CDF. And now substitute for y, capital Y equals capital X squared. It's the probability that capital X squared is less than or equal to y. Since capital X is always positive, this can only happen if x is less than or equal to the square root of y. In terms of the cumulative distribution function of capital X, this is f of the square root of y. So evidently the cumulative distribution function of capital Y is the square root of y, provided that y is in the interval from 0 up to 1. When y is negative, the probability that y is less than a negative number is obviously 0. When y is 1 or more, the probability that y is less than or equal to 1, or any number greater than that, is equal to 1. Here's another example involving generating a uniform on 0, 1 from a random variable with a completely different distribution. Suppose x is a continuous random variable with a probability density function f of x of the form 1 over 1 plus x the quantity squared. This holds for x greater than 0, but when x is negative, the probability density function is 0. Consider the random variable y equal to capital F of x. Notice that the random variable x has CDF capital F. So the transformation, the new random variable y, depends not only on the random variable x, but on the CDF of that random variable, capital F. Of course, we get the cumulative distribution function, capital F, by integrating the density function, 1 over 1 plus z squared, from 0 up to x, provided that x is a positive number. My objective here is to try and determine the distribution of that new random variable y equals f of x. Towards the solution, we'll try and find the inverse function of the CDF capital F of x, which when we carried out the integral, defining the CDF, we discovered it was 1 minus 1 over 1 plus x. This is a strictly increasing continuous function for positive values of x. As such, it has a well-defined inverse function. To find the inverse function in general, we fix some positive value of z and attempt to solve the equation f of x equals z for x. In order to be able to find a solution, we need to choose a value of z less than 1, because f of x never goes above the level 1. So we begin by writing the equation f of x equals z, 1 minus 1 over 1 plus x equals z, and then reorganizing it by moving the z to the left and the 1 over 1 plus x to the right-hand side of the equation, taking reciprocals on both sides, and then subtracting 1 on both sides to obtain x equals z divided by 1 minus z. We have discovered the inverse function. F minus 1 of z is z over 1 minus z. And of course this only makes sense provided that z is strictly less than 1. We're now in a position to try and find the cumulative distribution function of y. And as usual, we begin by writing down the definition of the cumulative distribution function, the probability that capital Y is less than or equal to little y. And if we now substitute for y is equal to capital F of x, we obtain the probability that f of x is less than or equal to y. Now since f inverse is an increasing function, we can apply it to both sides of this inequality without otherwise changing the statement or the probability. So this is identical to the probability that f inverse of f of x is less than or equal to f inverse of little y. But f inverse of f of x is just x. That's what we mean by an inverse function. I'm left with the probability x is less than or equal to f minus 1 of y. By the definition of cumulative distribution function of x, this is f of f minus 1 of y. Again, because these functions are inverses of one another, that's just y. What have we discovered? Probability that capital Y is less than or equal to little y is equal to little y. This is true for all values of little y in the interval from 0 up to 1. What distribution do we know with that cumulative distribution function? There is only one. That's the uniform distribution on the interval from 0 up to 1. The random variable y must have a uniform on 0, 1 distribution. So let's recap. We took a random variable capital X, a continuous random variable, defined a new random variable y equals capital F of x, where f was the CDF of x. We discovered that the new random variable y was uniform on 0, 1. This is true not just for this distribution, but for any continuous distribution. Every continuous random variable x can be transformed into a uniform on 0, 1 by using its own CDF. Example, generating a random variable with a CDF capital F of x using a uniform. This is exactly the reverse process of the one we've just described. And, in fact, it's an integral part of virtually every software package that does simulation. Computers are very efficient at generating random variables that are approximately uniform on the interval from 0 up to 1. Nearly all other distributions and virtually all simulations are conducted by transforming these to get the distribution that you require for your given problem. Let's go back to the last example. We discovered that y equals f of x is a uniform on the interval from 0 to 1. Of course, if we have an inverse, f minus 1, and apply it to both sides, this equation is equivalent to the equation x is equal to f minus 1 of capital Y, which is an equation relating a uniform random number y to a random variable x having a cumulative distribution function f of x. This is at the very heart of random number generation. The theorem goes as follows. If y is a uniform on the interval from 0 up to 1 and capital F of x is a continuous increasing cumulative distribution function, as such it has an inverse function, f minus 1, then suppose we define the random variable x to be f minus 1 of capital Y. Then that new random variable x has the cumulative distribution function f of x. If you started with an exponential cumulative distribution function, for example, this process would give you a random variable which has that exponential distribution. The proof is very simple and in fact a repeat of the calculations we made on the previous slides. What's the probability that capital X is less than or equal to little x? Substitute capital X equals f minus 1 of y. And then this inequality remains the same provided we apply the continuous increasing function f on both sides of it. F of f minus 1 of y is less than or equal to f of x, where again f of f minus 1 of y is just y. So this is the probability y is less than or equal to f of x. Y is a uniform of interval from 0 up to 1. The probability that y is less than or equal to f of x is the probability that it falls in an interval from 0 up to f of x. And for a uniform, that's the length of that interval, f of x itself. What we've shown is that the random variable x, therefore, has cumulative distribution function, capital F of x, which is what we wish to show. Here's an example. We wish to find some function of a uniform random number, y. I've called it little g of y. X is equal to g of y should have a probability density function given by little f of x equals x over 2 when x is in the interval from 0 up to 2, and 0 elsewhere. Solution. The first step when dealing with transformations of random variables is to begin by calculating the cumulative distribution function, capital F of x. That's obtained, of course, by integrating the probability density, and in this case, that gives us x squared over 4 when x falls between 0 and 2. The next step is to find the inverse of that function, x squared over 4. And we do that as we did before, by setting x squared over 4 equals y and solving for y. The solution, in this case, is the square root of 4y, provided that y falls in the interval from 0 up to 1. So by the last theorem, the generator we're looking for is x equals the square root of 4 times y where capital Y is uniform on the interval from 0 up to 1. We can rewrite this as 2 times the square root of y. Before you leave such a problem, you should check to make sure that it's a random variable in the correct interval. In this case, as capital Y runs from 0 to 1, 2 times the square root of y runs between 0 and 2. So at least the distribution is supported on the right set. The answer to the question, therefore, is g of y equals 2 times the square root of y. Review problem 1. Find a function x, some function of y, where y is uniform on the interval from 0 up to 1, so that x has a given probability density function. This is a triangular density. Little f of x equals x when x is between 0 and 1, and 2 minus x when x is between 1 and 2. Elsewhere, f of x equals 0. Solution. Again, the first step is to establish what the cumulative distribution function is, capital F of x. It's obtained by integrating the probability density function, but in this case you have to be a little careful, because when x is less than 1, you just integrate the value of z from 0 up to x. But when x is between 1 and 2, you need to integrate up to 1 first, plus the integral from 1 up to x, because in these two regions, the probability density function has a different form, z in the first and 2 minus z in the second. It turns out that when x is less than 1, it's 1/2 x squared, and when x is between 1 and 2, it's minus 1/2 x squared plus 2x minus 1. Now, inverting such a function might seem like a bit of a difficult exercise, but again, you have to invert it differently depending on whether y is less than 1/2 or bigger than 1/2. I've written down the inverse here. And of course, the random variable that we're looking for is capital F inverse of capital Y, or g of y. It's the square root of 2 times y, when y is less than 1/2, 2 minus the square root of 2 times the quantity 1 minus y, when y is between 1/2 and 1. Review problem 2. Again, I'm given a uniform random variable on the interval from 0 up to 1, call it y, and we're looking for a function, g of y, x equals g of y, so that x has a probability density function 3x squared over 8. Solution. Again, we begin by working out the cumulative distribution function. This is obtained by integrating the probability density, and it's 1/8 x cubed for x in the interval from 0 up to 2. That's the exciting bit. The boring bit is 0 or 1, depending on whether x is less than 0 or bigger than 2. Again, we need to find the inverse of f, so we solve f of x equals z, where z is in the interval from 0 up to 1. That gives us 1/8 x cubed equals z. And solving that, x is equal to 2, z to the power 1/3, the cube root of z. So the random variable we're looking for, the function we're looking for, is g of y equals 2 times the cube root of y. It has the required cumulative distribution function.